Okay, now that we've had our Stella demonstration and everybody knows everything they need to know about Stella, well, maybe almost everything, I want to move on into the heart of my presentation and talk about the evolution of Ecofish.fish. Ecofish.fish is the precursor of Ecofish. Ecofish.fish is a Stella model, a good deal more complex Stella model than the one I just showed you. But all of the components that you saw before, all the components that are here, or many of the components that are here, are the same ones that you just had a look at. This is a picture of the Stella model that we call Ecofish.fish. This is actually figure 1 in a long manuscript that I've been developing with the help of a bunch of folks, including John Miller. This model is faithful to Fry's tenet in that the effects of environment over here, the 4 variables that we've talked about, oxygen, temperature, salinity, and pH, the effects of those environmental variables are on metabolism, and then the output from metabolism is the thing that affects the activity of the organism, represented by standard bioenergetics model. So our model has 2 sectors. The top one up here is metabolism, and there you can recognize the 5 classes of Fry's physiological classification of environment. Here you can recognize active and standard metabolism as a function of those interactions in those 5 classes. And the output is metabolic scope for growth. And if you look, you'll see that crossing the barrier between metabolism and bioenergetics in that direction, there is only a couple of arrows. Connectors coming from metabolic scope for growth and other components of metabolism. There are several arrows going the other way, and those arrows are primarily the scaling effects of fish weight on these interactions of environmental variables with metabolism. This basically is a model for fish growth as a function of time-varying environment. It accommodates variation in the 4 physical-chemical variables that you see there on the left. It also accommodates variation for some potentially biotic variables, factors associated with feed, like how much feed there is available and the extent to which it's natural forage or paired feed, the digestibility of the feed, the gross energy density of the feed, all have effects on the way feed energy is translated into fish energy by way of food consumption here. And then the energy pool is distributed among respiration, waste down here on the bottom, and the overhead, the processing costs for handling the food. We call it SDA. And then, by the way, sort of as an afterthought almost, as a resultant, in fact, what's left over gets translated into new fish. The weight of the fish is a resultant. The growth of fish is a resultant under this standard bioenergetics model. So that's the model, and I could spend a lot more time picking through it with you, but I think the important thing is to get on and let you have a look at how the model was built and have you decide how good a model is it. Does it do the job it was intended to do, which is to simulate fish growth primarily as a function of environmental variables. So the model was built around this guy. This is the red drum. We've done lots of tank experiments and pond experiments with red drum because in Texas, red drum is not only an important sport fish, it's also an important aquaculture species for food production. We've done experiments like this one done by Cynthia Hutchins, one of my students. Cynthia grew red drum experimentally at temperatures ranging from 18 to 32 degrees from this starting size. It looks like about 6 grams or so. And then several weeks later, she measured the weight gains, and what she found were these two curves, and I've represented reality in two different ways, best and average, and I won't go into the detail about that, but the thing I want you to do is focus on the comparison between the simulated final weight, which is curve 4, and by the way, these are standard, as you now recognize, standard Stella outputs. Notice that the simulated weight of the fish corresponds pretty well with the observed weights as a function of temperature, and you can see that growth obviously was faster at temperatures around 28, 29 degrees than at either higher or lower temperatures. Cynthia also measured metabolism of the fish while they were actually in their tanks using open system respirometry. And the blue line here is the set of values, and you can see there is the obvious Arrhenius effect of increasing temperature. I think the Q10 for this was about 1.7. The blue is the observed metabolic rates of the fish, and the red and the purple are respectively the simulated maximum or active metabolic rates and standard rates. So you can see the fish in these tanks were perking along with routine metabolic rates that were on the high side of their metabolic scope. We also went into the field. In fact, these are old data from another former student, Umberto Garces, collected several years before we began to build Ecofish.fish. These data were collected from pond grow-out trials down in Panama conducted by a commercial company, and graphed here as a function of time. And again, time is pretty extensive, 8,000 hours. That's about 11 months. There is temperature in purple, and temperature is relatively constant over this 11-month period. Didn't vary much because this is, after all, an equatorial site. But like a lot of equatorial sites, there's a pronounced wet and dry season, so you can see that salinity went as low as about 10 parts or 8 parts, and then as high as about 40 parts during the dry season. So the most pronounced cycle here is salinity. Dissolved oxygen concentration, and this is early morning measurements measured daily and then averaged over 2-week periods, sort of declined over the course of the grow-out period, reflecting the increase in biomass of fish, as well as the increase in the wastes that accumulated in the ponds. Okay, again, direct your attention to the goodness of fit. The blue is the observed weight of the fish over 2-week intervals, and the red is the simulated weight. And except for this one little period in here, the matchup is really good. These are what we call parameterization experiments. We build the model according to the rules as Fry laid them down and as we interpret them. Then we find the numbers that are required to make the model fit through parameterization trials like these. And when we get all done, and here's some other experiments that I didn't show you. Maida Umberto is this last one, and TA1 Synth was the one I did show you. There's Steve Craig's salinity experiment, another temperature experiment done by Cynthia, and Chris Stahl's dissolved oxygen experiment. Here we've graphed the percent change in weight observed for each of the treatments involved in each of these several trials against the percent change simulated. And if in fact there was perfect agreement between observed and simulated responses, we would have an equation here of y equals 1x plus 0, and it's doggone close to that. So what does this prove? This proves that it was possible to find constants to put into Fry's model as we interpret it. It's possible to find constants that give good agreement over these 5 parameterization trials. That doesn't prove that the model is going to work when one goes back into the laboratory or the field and does actual tests of the model. So that's what we did. We started to perform a series of cage trials in the field. There's another one of my students, Robert Vega, and his partner and colleague in Parks and Wildlife, Ruben Chavez. And what Robert and Ruben are doing there out in Corpus Christi Bay is they're putting out these cages that are 1 meter deep by 1 meter in diameter. Some of the cages are divided into 4 wedge-shaped compartments, as you can see here, so that we can compare fish that are separated from one another with fish that are together. We also did manipulations of habitat to try to assure some variation in environment, just to guarantee that there was variation. We also went into the lab and made measurements on metabolism of the fish using an automated respirometry system. Another of my students, Lance Fontaine, sitting here at the computer monitoring these experiments. This is a computer-controlled automated system. And then we took these data and put them together. We took the growth trials that we did in the field, and we took the respirometry data from the lab, and we took this ecophysiological model, ecofish.fish, and used it to interpret these data. And then finally, we compared the observed change in weight with the values that were simulated under the model. And this is the kind of goodness of fit that we got. This happens to be growth in that pond I first showed you for the 13-month trial where there was so much variation in environment. This is the actual growth of 3 real fish held in 1 meter cages like those you saw and fed every day all they could eat, good shrimp, this brown and the green and the blue. And then here is a simulated fish that starts out at the same median weight as these 3, about 13 grams, and ends up 13 months later in the group with a weight of around 1,700 grams. So when you take what we think was a conservative subset of all of the field tests that we've done, a fairest comparison, we arrive at not as good agreement between observed and simulated weight change as you saw for the parameterization trials, but still pretty doggone good agreement. Here are 4 independent trials done by Robert Vega down in Corpus Christi. One of those is PTO4. That was the one in the 13-month trial you just had a look at. And the R-square for all of these treatments from these 4 trials is up around 80.8. So we're explaining about 80% of the variance in percent change in weight over time, which we think is a pretty good accomplishment. I don't think there's any other model that can accommodate environmental variation like have gone into these simulations and do as good a job of predicting performance of fish. Okay, so what have we learned from this modeling effort? What we've learned is that it's not hopeless. For a long time, I had about decided that understanding the variation in fish performance was a hopeless task. That the complexity of the interactions simply made it impossible. But I don't feel that way anymore. I think Ecofish.fish has taught us that it's possible to make sense of environmental variation. But if you're going to do it, you do have to systematize your knowledge. And the only practical way to do that is by using mechanistic models, using software, not necessarily Stella, but some sort of simulation software. Another lesson is that ecophysiological modeling and these assays using automated respirometry can be used to partition the variation in growth between the part that is due to ordinary variables and the part that is due to extraordinary components of environment that I call worrisome, toxins, pollution, and that sort of thing. But here's the good news. Coming out of studies both in freshwater with bluegill and marine systems with red drum, it looks to us now that in natural and aquaculture systems, typically most of the variation, a large part of the variation in growth rates of fish, and therefore by extension performance generally, is attributable not to these mysterious components of environment that we have a hard time even knowing that they exist, much less being able to measure them, but rather to the ordinary components of environment. The ordinary components I'm thinking of are temperature, dissolved oxygen, and salinity. Those account, I think, for most of the variation we see in performance rates. Okay, well, I guess I'm trying to move in transition now from Ecofish.fish, the research model, to Ecofish, a model that grew up with the research model at its core, but incorporates a lot of additional features that are especially designed for teaching. I am working as hard as I know how to take what I have learned over my career, and a good many of my colleagues have learned, and using this approach, putting all that together as a tool to help ordinary folks, citizens, as well as future scientists, you students, understand the connections between environment and fish biology and production. The outcome has a core of Ecofish.fish, but I warn you, it's a lot more complex than the research model. It's even beginning to look like a fish. See how evolution works? Here is Ecofish, the star of 417, Biology of Fishes. And if you look very carefully, you can recognize the ancestral core. Here, this sector, you can see the 5 classes of physiological effects here. Excuse me. So this sector is metabolism, and down here you can barely make out that this is bioenergetics. Everything else has been added. Everything else has been added so that we can use Ecofish as the virtual subject in experiments that we do in Biology of Fishes course. Ecofish never complains. Ecofish provides an endless supply of willing subjects for these virtual experiments. These experiments are producing results that are realistic as I know how to make them. They're stochastic results. Ecofish.fish is a deterministic model. Given X input always results in the same Y output. Ecofish, on the other hand, is a stochastic model. It has natural variation incorporated so that one gets not the same result every time, but a distribution of results around a mean that's reasonable. Ecofish doesn't die unless we want it to, and if it does die, it doesn't smell. It never produces dead fish or frustrating failures of equipment. And it doesn't require that students be present in real time in the teaching lab, which is a really handy thing given the dispersion of education geographically now. I tell my students, Ecofish feels no pain. It's up to you and me to feel its pain for it. This makes the people who run our animal use protocol committee very happy. But the most important thing about Ecofish is that it does help students. I'm convinced of it now after a couple of years' experience. It helps students understand that the isolated facts and figures that they have come into contact with both as students at the university and out there in real life, that those facts aren't just bits and pieces of information that can be randomly organized or not as you please. Those pieces of information, if they are organized using a systematic approach like Ecofish, suddenly everything ties together and makes sense. And when things tie together and make sense, then problem solving becomes a much easier job. Okay, I'm going to actually bring one of the versions of Ecofish up and go through a little demonstration of what I think is the most interesting lab that we do in biology of fishes. So I'll cut away and bring Stella back up now.